this leaving off. So I'm hoping you remembered and you have handy, you might flip back and forth at what we talked about yesterday, or Monday. So we talked about oxidation numbers, and as we talk about this, like between my two hands, I hope you can see a reaction arrow. Okay, it might be an equilibrium arrow, or it might be just a one way. So from the left to the right, okay, if something increases, and now this is an atom because we assign oxidation numbers to atoms. If the atom from the left to the right, if it increases in its oxidation number, then we can say it was oxidized. Oxidation occurred, okay? If you look, compare the left to the right, and actually over here on the product side, that atom has a lower oxidation number, it could be negative or it could be less of a positive one, then that means that that atom has been reduced. Okay, so that's it. And in tomorrow's exercise, we're going to be dealing with balancing, bless you, we're going to balance chemical equations. You're like, well, we did that in Gen Chem 1, and we did. But we're going to balance chemical equations, and actually they're going to be chemical reactions occurring in aqueous solutions, and we're going to be adding water molecules, hydrogen ions, okay? So if this redox reaction is occurring in an aqueous solution, then we can actually see, I'm trying to make a big deal of this because it's going to continue on. So when it says oxidation, let me see if I can make this sit down. Do this. I told you oxidation is where it gets a higher oxidation number. So what I want you to think of when we talk about oxidation is this. I want you to think of, say for instance, we had something, element X, and it was at a +4, okay? And if it was oxidized, that element now over here is going to be a +6, okay? And it went from a +4, and in between here we have, I hope this is going to work for you. Do you see where there's a difference of 2? It like went up in oxidation number by a difference of 2. Check this out. It did that. When it did that, it actually released 2 electrons. Kind of went, it like took negative 2 away, which is actually adding 2. So if I go over here, I'll call this Y, this thing is going to be reduced. We could say again a +4, but let's just say, wow, let's say it went on the product side, that same atom now has a -2. Does it look like a step down oxidation number? How many electrons? Mm-hmm. So here, it took 6 electrons in. 6 electrons were consumed to make that reduction occur. Okay, so that's kind of what we got going on. Okay. So, a lot of times your atom that's being oxidized or reduced is embedded, is an atom part of something larger, a compound, okay? So the overall reactant that has the atom that is being oxidized, okay, we say that that element is undergoing oxidation, excuse me, not element, but that reactant is undergoing oxidation. If species, whether it's a polyatomic ion or a compound, contains the atom that is being reduced, okay, we say that the reactant is being reduced. I will warn you that, and I think we're going to look at an example tomorrow, it's possible that you have one species and actually it has the thing that's being oxidized and the thing that's being reduced, the product side. So that's kind of exciting. So, but like this says, start to kind of get in your thinking, when oxidation occurs, electrons are released, okay, and when reduction occurs, electrons are consumed. Okay. Now this was the one that just kind of drives me nuts. The word agent means to kind of, like if you go to a travel agent, you let that travel agent help you make your travel plans. Okay, so the agent is helping it to happen. So if something is an oxidizing agent or oxidizing reagent, an oxidizing agent, it's not oxidizing like your travel person doesn't go traveling. It just helps you travel. So an oxidizing agent helps something else to become oxidized.
So it's almost like a catalyst?
It's kind of, because it facilitates. It is kind of like a catalyst. But the weird thing about it is, what we're going to see is if it helps something else oxidize, this drives me nuts. It's the thing, actually, an atom there is being reduced. So it's an oxidizing agent, and it's the thing being reduced. Like semantics. This, in fact, I almost wrote semantics on this. So the oxidizing agent contains the atom that's being reduced. So oxidizing agent and reduced reactant they go together. So then these other two go together. An agent of change. So if something is a reducing agent, it's not being reduced, it's helping, like you said, like a catalyst helps facilitate reduction. And in the meantime, as it's helping to facilitate reduction, it's being oxidized. Yep. I just think there was an easier way when they first set this up. Okay? But you're going to want to kind of get that semantics somehow. Okay, now combustion reactions don't occur in aqueous solutions, but let's just take a look at what a combustion reaction might look like. I think I said the other day, a combustion reaction is where, you basically, if you're combusting a hydrocarbon, you have carbon dioxide and water formed as your products. It's also a redox reaction. So let's see how this works.
When heated iron comes in contact with gaseous oxygen, a redox reaction occurs, producing iron oxide. The iron is oxidized and the oxygen is reduced.
So let's look at the equation and see if we can kind of see that oxidation and reduction as we kind of assign oxidation numbers to the reactants and the products. So here we go. Before we answer these blue questions, I know, this is the video that you saw. And I have to kind of change. I'm like, yeah, so oxidation, you get carbon dioxide and water. Well, that's the oxidation of a hydrocarbon. So oxidation here is we're going to oxidize iron. So let's see. I'm going to go back and forth. I'm going to pick on you guys. We'll start with Quaid, because Mike's not here. So let's go with this guy over here. The iron. What oxidation number can I put at the top there?
Metals.
But it's not a cation. It's a neutral metal.
So it'd be 0.
It is 0. Very good. Yep. You got it. So I'm going to put 0 there. We're going to go across. Okay, so Olivia, what do you think about the O2?
Was that +1 or is it 0?
It's also 0, yep. And you know it's 0, let's see, because it's in its uncombined elemental form. Like if it had been H2O, then it would have been -2. But now it's not combined with anything else, so it's just 0. Okay, Quaid. So, to me, we need to do something with the Fe and the O on the other side. So I'm going to start with the O, and then I'm going to give you the Fe. So what is that oxygen? What's this guy right here?
Always -2, right?
Yep, we're going with -2. It is -2 because you could hang your hat on that. -2 because it's combined with something else. Okay, so we can do the math down here. So this is where I went. I went 2 times question mark, whatever that oxidation number is, plus 3, because there's 3 oxygens, times -2 has to be equal to 0. And the reason it's 0 is this is a neutral molecule. So what is that question mark, Olivia?
It's going to be +3.
I'm liking it. +3. You got it. Perfect. Let me switch the color of my pens here to blue. Okay, so now the way this works is something needs to be oxidized, something needs to be reduced. So, back to you, Quade, what is being oxidized? Look on either side of the reaction arrow.
Oxidized means increasing in electrons, correct?
Increasing in oxidation number.
Which means it becomes more negative, right?
Nope, becoming more positive. Yep. Yep, and kind of like, I think what you said, Quade, is it's giving up electrons. So oxidation, and we're going to be looking more at that, but it's giving up electrons. Very good. We're not going to count the electrons yet, though. Cool. Well, what's being reduced? The O2. It's going from a 0 to a -2. All right, so let's answer these. So you guys answered the first two already. So which atom is undergoing an increase in oxidation number, the Fe? Which atom is undergoing a decrease in oxidation number, the O, the oxygen? But I really, you know, if you're faced with this, I'm a firm believer in just going across and assigning oxidation numbers for everything and going from there. Okay, so Quade, which reactant is being oxidized? So reactant to me steps back, it's not just the atom, but which reactant? Which could be the same as the atom. Yes, very good. Fe solid, perfect. So which reactant, again, is kind of could be step back, which is being reduced? The O2, perfect. Okay. So now, Quade, which reactant is the oxidizing agent? Nope. Because it's helping oxidation to occur. It's not being oxidized itself. So it's probably being reduced. It'd be what? Yeah, exactly. It's the O2. Perfect. And then, so what do you think, Olivia? Last one? The Fe. Yep. So you see how that kind of goes together. The thing that's being oxidized is the reducing agent. And the thing that's being reduced is the oxidizing agent. Like I said, I just kind of throw up my hands.
Backwards.
Well, the agent just helps it happen, and if it helps it happen, it does the opposite.
Well, is it just because of the fact that it couldn't become oxidized without it, and so that's why it's called?
Right, right. And the thing about, it kind of goes along with this, anytime somebody says, oh yeah, that's a redox reaction. Well, you know something's being oxidized and something's being reduced. It has to be that. They have to go yin and yang.
Is it always like this for, like reactions, or is it just kind of depends? Like,
Oh, see, yeah, there's,
yeah,
right. Chemical reactions can have different driving forces to make them spontaneous. Chemical reactions can just have different things that are going on. Like if our one of my favorite ones is where the cation and anion switch partners. Okay, that's just an ion exchange reaction. There's no redox occurring there. Nothing. If you were to look on either side of the reaction arrow, they have the same oxidation numbers.
Okay, so that's what I was wondering.
Yep.
So the oxidation numbers are just the same on both sides.
Yeah, for that type of, yep. So it's just another type of chemical reaction, but an important one. So here we have some pictures. I think you guys did the copper lab last semester. So that's what this is actually talking about. We're going to kind of look at this down here. Now you might say, well, that's an ion exchange reaction. But if you look at it closely, we have zinc solid, and we have zinc over here that's a plus, plus 2. Zinc plus 2, okay, over here. How do you know it's a plus 2? Because it's part of a salt, zinc sulfate. It's no longer, this is going to be 0, this is going to be plus 2. So you're like, dude, I already know I got something, I have something being oxidized, so I bet something's being reduced. So let's see. Let's go. I think we're back to you, Quade. What oxidation number is the zinc? Zinc solid. 0. Perfect. So Olivia, this is copper 2 sulfate. And actually the SO4, well, what's copper? Then what's the oxidation number of copper there?
Is that plus
No. And we know,
What's the rule for that?
we know it's +2
Okay.
because, and copper could be a +1 or a +2, but do you see, we know it's a +2 because we know sulfate is a -2, and there's only one.
Oh, okay.
So it kind of goes back to a Chem 1 thing. Yep. So above the copper, I'm gonna put +2. Cool. Now, I'm gonna go ahead and take sulfate over here, down here in this corner, SO4, 2-. I wouldn't actually have to do this because honestly, can you see sulfate is the same, it's the same on both sides. So we know that sulfur oxygen actually aren't doing any oxidation reduction, but it's a good little exercise. So, Quaid, what is the charge on each of those 4 oxygens? Not the charge, I'm sorry. What's the oxidation number? And it goes back to the rule we've been using. It's a -2, yep. I'm going to put a question mark over the sulfur because sulfur can do a couple different things.
Does that make the sulfur 6 then? It's -2 charge.
I'd have to do the math, probably though. So what Quaid's saying is a +6, do you agree too? I think, okay, so you're right. I didn't have to do the math down there. I buy that. Perfect. You got it. So let's go ahead and put +6 and -2. Okay, Olivia, what do you think about the zinc?
The zinc is going to be +2.
Yep, very good. And these are still +6 and -2. So Quaid, what about this copper over here? 0, oxidation number 0, perfect. Yay. Okay, so Olivia, which, I know it says reactant, but let's start with which atom. Now, do you guys see where an atom and reactant are different? Okay, atom is the atom, and reactant is kind of the thing the atom's in. Okay, Olivia, so which atom is being oxidized? I'm liking it. The zinc's going from a 0 to a +2. So oxidation, perfect. So Quaid, what's being reduced? That copper, perfect. It's gonna go from a +2 to a 0. I'm liking it. Very good. Okay, so now back to the questions. So what do you think, Olivia? Which reactant is being oxidized? So the reactant is the thing it's in, not necessarily the atom, although it could be. Which reactant is being oxidized? It is the zinc. Yep, zinc solid, perfect. Which reactant is being reduced? Oh, sorry, Quaid. Yep, and actually I think you're gonna see that since it's an aqueous solution, I'm just gonna put the Cu +2, even though it's the copper 2 sulfate, so. Okay, so Olivia, which reactant is the oxidizing agent?
Is it the whole thing or is it just the copper?
Yeah, I would just go with just this because it ionizes water.
Okay.
Yeah, so the point is that you're going with the Cu +2. Very good. So which reactant is the reducing agent?
Zinc.
It would be the zinc. Perfect. Very good. What else we got? They're kind of fun, I think. So I have a video. So one of the things, actually part 5, we're going to talk about are batteries. Cute little batteries. So batteries operate things by basically electrons flowing, and the reason electrons flow is because of a redox reaction. Is that not cool or what? Okay, so let's see what we got.
In an alkaline battery, zinc metal at the anode releases 2 electrons to form zinc oxide under basic conditions. The 2 electrons are transported to the cathode, where manganese dioxide is reduced from the +4 to the +3 oxidation state. Hydroxide ions are transported from the cathode region to the anode region of the battery.
Now, some of this whole battery stuff will make more sense later, but you kind of got a sense for electrons being given up at where, let's see, given up at where oxidation is occurring, and electrons being consumed where reduction is occurring. So, all right. Uh-oh. not real smooth at this yet. Okay, so let's take a look at this one, shall we? So, can't remember who we left off with. Okay, so what do you think about the zinc? What's its oxidation number?
0.
I'm liking 0. How about, now for this guy, I'm going to put a question mark over the Mn, and so Quaid, what is the oxidation number of the oxygen?
Negative.
-2. And so what do you think, Olivia? What's the oxidation number for the manganese, Mn?
+4.
+4. Do you buy it? Quaid buys that, I'm sure. Very good. Okay, let's go over here, and actually we could go either zinc or the oxygen, so let's go with zinc. What's the oxidation number for zinc? It's +2, and for oxygen? -2. Now the reason I said either one is zinc is always going to be +2 when it's an ionic compound like that. So let's go on over, I think we're ready for, Quaid, you're back to what's oxygen. See, to me, I'm going to put a question mark here over the manganese. So what's oxygen again? -2. So Olivia, then what does that make the oxidation number for the manganese?
+3.
+3. What do you guys think? Isn't that fun? Okay, so Quaid, what is being oxidized? The zinc. Perfect. So Olivia, what atom is being reduced?
The
Manganese. I'm liking it. Mn goes from a +4 to a +3. So, you know, here's a good example of, I mean, it just got bumped down 1, but by golly, it's being reduced. Very good. All right, some more examples.
The reaction of zinc and hydrochloric acid is both a gas-forming and a redox reaction.
And the next one.
When a piece of copper metal is placed in a solution containing silver ions, solid silver crystallizes on the copper. While the silver crystals grow, copper ions are also released into solution, giving the solution a blue color.
What's that?
We should do that one.
I was trying to think that might have been part of our copper lab. It's neat though, isn't it? So this was one, and this was the other. So let's just knock these out. They're so fun. So kind of from left to right, what do you think, Quaid? What is the zinc up here? What's its oxidation number? 0. Let's see. H and Cl. I think we go either way. So what do you think H is? What's the oxidation number?
+1.
It is a +1. I think that was one of our rules. So Quaid, chlorine? -1. Olivia, zinc, how about zinc over here?
+2.
I'm liking it. So Quaid, what about zinc, what about chlorine over here? -1, perfect. Olivia, what about oxygen here?
+1.
Nope. Uncombined.
Oh, 0. Okay, sorry.
0, very good. Thanks. So Quaid, what's being oxidized? The zinc. Zinc, I'm liking it. Olivia, what's being reduced?
Hydrogen.
Hydrogen, perfect. So we're going to switch it up and we're going to start, because we keep getting the same one. So Olivia, from left to right, what's copper here?
0.
It is 0, very good. Quaid, what is the silver ion here? +1, I'm liking it. Olivia, what's the copper here?
+2.
+2. Quaid, what's the silver here? It is 0. Olivia, what's being oxidized?
The copper.
Yep, perfect. So Quaid, what's being reduced? Silver. So one of the things, and I can't remember if, how do I say this? So there are different types of reactions. One type of reaction is it forms gas, okay? Another type of reaction is a precipitation reaction. Do you guys buy this? I mean, this is a precipitation reaction. How do we know? Well, we start with actually we start with solid, we have a different solid. Sometimes this is called a type of plating. So, okay, what else we got? Another one. Videos galore.
When pieces of aluminum foil are placed in a beaker containing bromine, a violent reaction occurs.
Woo.
The elements react to produce aluminum bromide, which consists of 2 aluminum atoms for 6 bromine atoms. It is visible as a white powder deposited on the beaker.
That's neat. So endothermic or exothermic? Exo, yep, for sure. So let's take a look at that one. We'll start again with you, Livia. So what do you think? What's the oxidation number for aluminum?
0.
What's that?
0.
It is 0, yay. Over here, the 2 bromines, what's their oxidation number? It is 0, very good. So Olivia, let's see. I think we could do either one there. So aluminum, what do you think? And actually you could use a periodic table and find where it is.
Is that +3?
It is a +3, perfect. So Quaid, what about those bromines? They're each a -1, perfect. So Olivia, what's being oxidized? Aluminum. So Quaid, what's being reduced? The bromine. Yep. By golly, I think you got it. You have it enough to do this. And I don't have the things to look at right now, so I'll just push them out there. They're fun. They set the stage for tomorrow's lab. So let's take a look at, oh, this is, I know how to do this. And show. Let's take a look at the next part. Yes.
Could we go back so we can write that stuff down?
Which stuff down?
Problems?
No, the balancing the redox reactions by half connection method. That was the last slide for that part.
Oh, thank you. Thank you. Got it. For sure. Okay. That was weird. The assignment slide is there. And okay. Oops, it's coming.
I was gonna say it had to.
There it goes. Okay, I'll put this whole thing up here. Okay, so this actually, I'm glad we went back to this, because this kind of sets the stage for tomorrow, part 4. And again, like I said, I'm going to skip that for now. I want to go to part 5 and kind of get a little bit of that under our belt. But we're used to balancing equations by inspection. And this is going to seem really tedious. And if I think of balancing equations this way, I'm going to show you tomorrow by the redox half equation reaction, or half equations. It's very tedious. But I think it's the only way you can balance in some cases. So
with the last one, how does the battery work? Since it's always equal, how does it still give off electricity?
It's a net equal, like if you look at, like if it's, but it has regions of high electrons and regions of low electrons. And then that's what we call a gradient. Anytime you have high here, high pressure, high number of electrons, low pressure, low number of electrons. So that electromotive force is basically electrons going from high to low. So when it says it's neutral, it just means like, if you were to look at, well, I just did that, I have high over here, high over low over here. If I were to basically say my system is this, then it's neutral. Okay, but within the system, I have regions of high and regions of low. Does that make sense?
So it still gives off electricity, but keeps all the electrons.
Right, right. They're kind of chasing themselves. Yeah,
Kind of weird.
it is weird. They're being created, they're being consumed, and then they're being created. Yeah. So it is weird. I know.
So batteries actually create electrons.
What's that?
So batteries create electrons then?
Batteries create electrons, and they flow through the device, and then those electrons are supplied to the other part of the battery. I know. I think so too.
Kind of cool.
That's very cool. Oh, the mighty electrons. Okay. We lost half the class.
Yeah.
Speaking of batteries, that's what's coming up next. Afraid to pause it because I may never get it back again.
So like a degree in chemistry, you could go into like solar power, stuff like that, 'cause it's cells and stuff.
Yeah, there's a lot of things like that. To me, it's really got, it's hardcore physics, and it's definitely got, you know, chemistry and physics definitely
Kind of
overlap.
coincide, but it seems like they're always arguing each other though.
They argue with each other?
It seems like it.
How do they argue with each other?
Well, I mean, like they agree in the end, but like for chemistry, you kind of ignore the mass of electrons and stuff.
True.
Like ambiguous.
They
but
do.
Physics, they need to know that.
Right, oh yeah, that's true. They do kind of argue. They have different,
It's how-
yeah. But the fundamental laws, and it makes it interesting. I think it's fun, but yeah. So cells like this would be definitely the chemistry that's going on, and also the physics of the subatomic particles and the circuitry and stuff like that. So electrochemistry. So there's two ways you can go with it. Now these, if you read them, you might have to read them a couple times. The battery, if you want to put battery down under electrolysis cell, that's what a battery is. We've been talking about batteries. We saw a little video about a battery. I'm going to look again at what's going on within a battery. So battery basically is going to use a redox reaction to create a flow of electrons. Skip to 5. This other one up here, a good example of the voltaic cell would be kind of a fun thing is the hydrolysis of water. You can take water and you can supply an electrical current, and you are using it in this way as a voltaic cell at that point to create hydrogen gas and oxygen. To me, that's what I think of.
And that produces electricity.
Oh, I got them mixed up, didn't I? Oh my gosh, okay. So I'll fix this, thanks. No, the battery goes up here to the voltaic cell, and this goes down here to drive a chemical reaction. Thanks, Olivia. My bad. Final answer. Voltaic cell is where you're using a redox reaction to produce electricity. And electrolysis cell, you are using electricity to drive a reaction. Thanks. So in order to have this free flow of electrons in a redox reaction, you need to have certain pieces to your electrochemical cell. And they have these common names. So we'll just pick on batteries, okay? Your battery will have an anode, and I'm pretty sure that's the pokey up part, not the flat part. You know exactly what I'm saying.
Yeah, I know what you're saying.
Okay. So you'll have an anode, and that is where the electrons are going to be released. Okay. And then you'll have a cathode, and that's where the electrons are going to be consumed. So electrons released now, and I'm real bad about memorizing things, so I just have to think around them, think through them. At the anode, if electrons are released, that's oxidation. Electrons are released. It's stepping up an oxidation number. Electrons are released. A good way, I think, is if you think vowels, like A is a vowel and O is a vowel. So anode, oxidation, they go together. That's where oxidation is occurring. Electrons are released. Cathode is where the reduction is occurring, and that's where electrons are consumed. Okay. Then you also need some way to connect your anode and your cathode, and that's what an external circuit does. This is the path that your electrons can take from where they're being generated at the anode and consumed at the cathode. Then the last thing you need, and actually this is, I think, kind of a subtle thing, I think, and to me it kind of talks a little bit about what we're talking about so no electrons they just keep reusing their electrons. And this is a salt bridge or some sort of bridge to basically make your, to return electrons. Okay, need to maintain a balance with charges. Need to return electrons from the cathode compartment to the anode compartment. Okay. So with all that in mind, here's a little video.
In a voltaic electrochemical cell, an oxidation occurs at an electrode called the anode. The electrons released at the anode travel through a wire to another electrode called the cathode, where the electrons are consumed in a reduction reaction. Anions are then shuttled through a salt bridge from the cathode compartment to the anode compartment. Otherwise, a net negative charge would build up in the cathode compartment. The negative charges move in a circuit through the cell.
All right, isn't that cool? Now, the other thing about this before I move on is, can you see, so this would be our external circuit, kind of the gray thing up there. Notice that little peg thing? Okay, that little peg thing shows electrons are flowing. It can actually, I'm pretty sure it can either go this way or it can be neutral, no flow of electrons, or go this way. Now, the more it deflects, that means the more the electrons are flowing. Okay, so that deflection thing is kind of important. And someone's playing their music. Okay. I think we looked at this one, but let's see it.
In an alkaline battery, zinc metal at the anode releases 2 electrons to form zinc oxide under basic conditions. The 2 electrons are transported to the cathode, where manganese dioxide is reduced from the +4 to the +3 oxidation state. Hydroxide ions are transported from the cathode region to the anode region of the battery.
This actually is kind of one of the things we'll be talking about in part 4 in tomorrow's lab. These are actually 2 half reactions. Can you see where this half reaction is creating electrons? So that must be what, the oxidation, right? This one is consuming electrons, so that's the reduction. So these are 2 half reactions. In tomorrow's lab, we're actually going to separate out and work them in half reactions like this. What else we got? So here we go. Down here at the bottom is the redox reaction that's happening in this cell. We have copper being what? Oxidized, silver being reduced, redox reaction. And you can see the external circuit. See, in this case, the voltage is 0.460. Okay. Notice that the potassium and the nitrate are just spectator ions. We have our salt bridge here where the nitrate will go over that way and the potassium will go this way. So for that cell that we just looked at, we could break it out into 2 half reactions, and they look like this. At the bottom of the previous slide, we had the copper solid reacting with silver ion to form the copper +2 and the silver solid. We could break it out and look like this. Now, one of the things we know about reactions, you see that line there, we're going to add those 2 reactions. And of course, is anything going to cancel?
The electron.
The 2 electrons will cancel, exactly. So this overall reaction actually matches what was at the bottom of the page. So there's an important shorthand notation in kind of summarizing these electrochemical cells, and they look like this. You read them from left to right, okay? And it's going to be the anode compartment and then the cathode compartment. So the anode compartment looks like this. So anode was oxidation. What's being oxidized? The copper is going from a 0 oxidation state to a +2. This double bar right here separates your two compartments. So then from the cathode compartment, and then we go ahead and say what's being reduced. And then again, we go to the reactant, silver, the product, so it's going from a +1 to a 0. So that's the kind of the shorthand notation. And if it's happening in aqueous solution, then so we have electrode solution, double bar separating the compartments, solution electrode. Well, I think this is going to be good. I want to finish up these last couple of slides because, like, why do those electrons flow? And I don't know, you might have stepped out of the room, but anytime you have, it's called a gradient difference. It happens in biology with salt across membrane cells. You know, hypotonic, hypertonic, I don't know what it is, but basically if you have a lot, and it happens with heat. If you have a lot of heat over here, not much heat over here, well, heat is going to flow from high to low concentration. So that's what's happening here. We have electrons are released during oxidation, and electron deficient over here. So by golly, the electrons are going to definitely want to get from region A to region B, and they're going to do that using that external circuit. Okay, so electrons flow, making things work. Okay, so that's it. They call that the electromotive force. So that little thing up the top, that kind of needle, will give you what's called voltage. Voltage is energy per charged particle, basically. So joule, of course, is an energy, and coulomb is a measure of charge. Coulomb, more specifically, it breaks down to look like this. 1 mole of electrons will have 9.65 times 10 to the 4th coulombs. Now this is, to me, not a lot of blada, 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 but it's stuff that I won't necessarily test you over. Although I think it's very interesting. Okay, that's my blank slide, so that's how far I wanted to get today. Perfect. So